Chapter 3.7 is entitled Optimization, and it's really a very common practical application of first and second derivatives, minimums and maximums, used really extensively in engineering and science applications and business applications as well. Basically, we're trying to optimize, which sometimes means maximize and other times means minimize some certain function, some certain value or function that we're dealing with. Maybe it's cost of production, maybe it's profit, maybe it's maximizing the size of some kind of a container that we can get out of a certain surface area or whatever. These problems, each one is kind of unique geometrically. So we want to draw a picture to help ourselves understand what's going on in that situation. We want to write an equation, so we want to figure out some kind of relationship between the quantity that we want to optimize and other parameters. And we want to write that in terms of one variable. So we'll see, I'll give you kind of an example of how we might do that. And then we're going to take the derivative, the first derivative, to find possible relative extrema, and then we'll use oftentimes the second derivative test to make sure that what we have is either a minimum or maximum depending on what we're actually trying to find. So a typical example is trying to maximize the volume of a certain container given a fixed amount of surface area. So here we have an open box with a square base, and we're going to use 108 square inches of material, and we want to think about what dimension will maximize the volume. All right, so we're going to start off with making a picture. Here's an open box. So there's no top to this thing. This is an open box, so it has 4 sides and a bottom but no top. And the volume is just the base, the area of the base, which is x squared, since we have a square base, times some height. And we know the surface area is 108. So right now I have volume in terms of x and h. I want to get it in terms of one variable. So I know an additional relationship is surface area. So if I think about the surface area at the bottom of that box is x squared, and each of the sides has an area of x times h, and there are 4 of them. So the surface area is that, and I know that's 108. I can solve this for h, and then I can use this and plug that back into the equation that I had for volume. And when I do that, I get my volume equation just in terms of x. So here I have x squared times h. I figured out that h was equal to this, and then I'm going to distribute this x squared here and factor out this 1/4. So we get 108x minus x cubed with a 1/4 as the coefficient. Now that's my volume. So I can distribute that 1/4 in there, and I can simplify that thing into 27x minus 1/4 x cubed. And I could rewrite that if I want to write it in descending powers of x. I could also rewrite it this way. So there's my volume. All right. Now think about what's happening here. I've already accounted for that fixed surface area in my relationship between x and h. So I have a fixed surface area. Now the volume of the volume of this open box is equal to this in terms of x. I'm trying to get as much volume as I can, so I'm trying to maximize v with respect to h. So I'm trying to find, with respect to x. So I'm trying to find the x values that will give me the biggest v I can possibly get. So what do I do when I'm trying to find relative extrema? I take the first derivative, set it equal to 0. So I do that. I solve for x. X is 36, so my x value is plus or minus 6. So if I think about the domain that I could have, my x value, the base, can't be any smaller than 0. It can't be equal to 0, or I wouldn't have a box. And it can't be any greater than the square root of 108. because if x was the square root of 108, then that would account for all the surface area of my box, and I would have no surface area left over for the sides. Right? So only one of these will work for us, and that is the x equals 6. So x equals 6 represents some relative extrema of v. I'm hoping it's a maximum because that's what I'm trying to find, but I really don't know that yet. So I could set up a table. I could set up, here's x equals 6, here's from 0 to 6, and here's from 6 to the square root of 108. And I could look at my first derivative, and I would certainly hope that I would get a relative maximum at 6. So if that were the case, I should get a positive first derivative. So if I look at this, if I plug in 6, I get 27 minus 3/4 x squared. So 27 minus 3/4 of 36 is positive. So that's good. So if I plug in, well, I get 0 if I plug in 6. If I plug in 5, or a number smaller than 6, so let's try 1, 27 minus 3/4 is definitely positive. All right. So then if I try a number larger than 6, say 7, 27 minus 3/4 of 49, 3/4 of 49 is larger than 27, so 27 minus that is going to give me a negative. So I can see that I do in fact have a relative maximum of v when x equals 6. Okay. Another way I can do that is to use a second derivative test. So I can find the second derivative of v, which is really easy to find. The 27 goes away, becomes a 0 when I take the derivative of it. Now I get negative 3/2 x. When I plug in 6, I get a negative 9. So my second derivative is negative. That means that v is concave down at x equals 6. So I get a maximum volume at x equals 6. Right? So the dimensions that would maximize the volume would be 6 by 6 by 3 high, and then the maximum volume is going to be 36 times 3. Is 108 cubic inches. That's pure coincidence that it came out to be the same as the surface area that we started with. So don't read anything into that. It just so happens that's the maximum volume as well.